Alright, welcome again to what I think I can confidently say are good choices. So I'm working on the LPIC, very close to test day for the first exam. This is going to be in two parts, kind of like the old school. I don't even know what the CCNA is now, but back in my day, which is forever ago, even though it was not that long ago. You needed to pass the CCNA. Well, you had the option to pass it in 2 or 1 parts, but you don't have the option here for the LPIC. You have to take 2 different exams. So right now I'm on 104.2. So all I've got to do is get to .7, and then I can take the first test. If I fail it, then I might have to. I might think then about like switching to something else because this method of making videos and reading from the learning materials is not going to be an effective method. And if we go back and look at the playlist, you can see I started this a long time ago. My first, I've been studying for 3 months. So if I study for 3 months, I make videos, I do pretty well, an hour a day or something like that, and it just leads to a fail. I feel like I just gotta get, so maybe I could even just do the Linux Essentials or something like that, but I feel like if I fail this, it would be better served to like pivot over to like AWS and just like maybe start lower on the tree, maybe like a juniper or something like that. I feel like just continuing down something that's just not leading to passing results is not a good choice. But hopefully I'll pass. So the most important thing is I got to get through all the learning materials. So let's waste no time and start with lesson 102. So 104.2. So this is also going to be about devices, Linux file systems, and file system hierarchy standard. Last lesson, 104.1, was just a mega lesson on partitions and file systems. So file systems are not partitions. They are things you create within partitions. And file systems, there are a lot of different file systems you can choose from, and no two operating systems use file systems. They read file systems. So like, note there's a lot of different choices of file systems for each operating system you have. You'll probably have a different file system associated with it. Linux uses the EX4 the file system by default. I think Windows is probably NFS. I'm not sure about that. But like flash drives are NFS. Flash drives are like FAT. And then there's like better FS for like large data processing. So file systems are a very comprehensive subject. All right, so the objective here is to maintain the integrity of file systems. Introduction. Modern Linux file systems are journaled. This means that every operation is registered in an internal log, the journal, before it is executed. If the operation is interrupted due to a system error, like a kernel panic, power failure, etc., it can be reconstructed by checking the journal, avoiding file system corruption and data loss. This greatly reduces the need for manual file system checks, but they may still be needed. Knowing the tools used for this and the corresponding parameters may represent the difference between dinner at home with your family or an all-nighter in the server room at work. In the difference between what? So knowing the tools used for manual file system checks. So like this is how you can tell what's going on in a really like easy, efficient way. So okay, so we're gonna learn about So in this lesson, we will discuss the tools available to monitor file system usage, optimize its operation, and how to check and repair damage. Alright, so checking disk usage. There are two commands that can be used to check how much space is being used and how much is left on a file system. The first one is du, which stands for disk usage. du is recursive in nature. In its most basic form, the command will simply show how many 1 kilobyte blocks are being used by the current directory and all its subdirectories. Okay, so if we do okay, so the current directory and all its subdirectories. So let's go into my lab and let's do some experiments here. So we're going to type in lab. Alright, and let's get some different values of du. If I do a pwd, you can see I'm home. If I do an ls, you can see I've got quite a few files in there. So let's do a du. Okay, so we can see du keeps going and going and going. That's because the command will show how many 1 kilobyte blocks are being used by the current directory and all its subdirectories. So it's recursive in nature. It goes through each directory, subdirectory, and files within the directory, I guess, and gives you this block. So here, obviously, this is an empty directory they're in. My directory is not empty at all. So let's create a new one called du test. And let's switch over to du test and then run du. And there we go. Now we get a similar result as they got. We get the blocks, and then we get this dot here. So this show, it's like the ls command. So if I do ls -a, see what we got here? We got a dot and then a number. So, it's a little bit. The output is a little bit similar to that. It's difficult to see the dot there, but let's go into another one. Let's go into my files. Okay, and do a du there. Okay, so we got 8. And let's go into one with some more files in it. Let's go into the Romeo and Juliet. It's only got one file, but it should be bigger than 8, hopefully. Okay, 172. Oops, I hit exit. So that takes me out of the lab entirely. Go into this wet ball project I was working on. So so it's recursive, so it goes through the Linux virtual environment as well, which would be nice if you could deactivate that somehow. But anyways, I think we got a basic sense for it. This is not very helpful, so we can request a more human-readable output by adding the -n parameter. Okay, so this shows how many 1 kilobyte blocks. Now this is interesting because it shows how many 1 kilobyte blocks there are, but we learned that you can adjust the block size, and by default the block size is 2048. So I've actually got a question. I've got a question for the AI, and we're gonna ask it right now. So the question is, so I've learned in the previous reading that file systems have configurable block sizes, and that the most typical block size is 2048. Why does du in the case of this example show how many 1 kilobyte blocks are being used? show how many 1 kilobyte blocks are being used. Would what DU shows change depending on how the file system is set up? For instance, if the file system block size was 2048, would DU show how many 2 kilobyte blocks are being used? What am I not understanding here? Or what am I not understanding? Okay.
You've raised a good point, and I'd be happy to clarify how the do command works in relation to file system block sizes. The do command reports disk usage in terms of file system blocks, not necessarily 1 kilobyte
Really?
blocks. The default behavior of do is to use 1 kilobyte blocks when reporting disk usage. However, the actual size of a file system block can vary depending on the file system and its configuration. In traditional Unix file systems like ext2, ext3, and ext4, the default block size is often 4 kilobytes, not 1 kilobyte. So when do reports disk usage in kilobyte blocks, it's typically referring to 4 kilobyte blocks on these file systems. If you have a file system with a block size of 2048 bytes, then do would indeed report disk usage in terms of 2 kilobyte blocks. The size of a block is determined by the file system itself, and do takes that into account. It doesn't always report in 1 kilobyte blocks. To summarize, do reports disk usage in file system blocks, and the size of those blocks is determined by the file system's configuration. It doesn't always use 1 kilobyte blocks, it adapts to the actual block size of the file system in use. So, if the file system block size were 2048 bytes, do would show usage in 2 kilobyte blocks for that file system. Your understanding is correct, it's a matter of how the file system is set up.
Okay. Show me examples of the do command for different for file systems. Show me examples of the do command for multiple file system configurations. Alright, this looks pretty good.
Certainly. Here are some examples of how the do command might report disk usage for different file system configurations. 1 default ext4 file system, 4 kilobyte blocks.
This is what we have here.
$do h/path/to/directory. 4.8 m/path/to/directory. In this example, the file system is using the default 4 kilobyte blocks, and do reports disk usage in human readable format, megabytes. 2 ext2 file system with 1 kilobyte blocks asterisk. $do h/path/to/directory.
Oh, I get it.
19 m/path/to/directory. ext2 file systems can have 1 kilobyte blocks. Here, do still reports in human readable format, but in this case, it's using 1 kilobyte blocks.
Yeah.
3 btrfs file system with 16 kilobyte blocks asterisk.
I don't get it.
$do h/path/to/directory. 3.5 m/path/to/directory. BTRFS is a modern file system that can have variable block sizes. If it's configured with 16 kilobyte blocks, do will report disk usage accordingly. 4 ZFS file system with variable block sizes asterisk. $do h/path/to/directory. 8.2m/path/to/directory. ZFS is another file system that can have variable block sizes depending on its configuration. Remember that the reported sizes by do depend on the actual file system configuration. The H flag is used to make the output more human readable by using units like megabytes, M, or gigabytes, G, but the
Oh
underlying
man, I'm
block
really
size will be
confused.
determined by the file system itself.
I am very confused by this. Okay, so by default, DU only shows the usage count for the directories, considering all files and subdirectories inside it. To show an individual count for all files in the directory, use the -a parameter. Okay, so we got du space -a and then h. So h is the human readable, so we've got the units right there, and then -a shows it for the files as well. So let's try that in my lab. So, and we're gonna move to something that's a bit nicer here. So maybe this animal. Yeah, okay, let's try that. So we got du. There we go. Now, the other thing is, like, I'm just having the number 4 show up. I don't understand that. So, I wish I was doing that in a different conversation. But anyways, there's du-h. We've got the units now, and it says 4.0. So if we do -ah, now we've got it for each file. And these must be, yeah, these are just empty files. Wish I had like maybe this experiments here. Yeah, let's do it with the experiments one. Okay, so these are empty files as well. But hey, that's a good way to see if they're empty files. Because if you use cat to see if something's empty and it's not empty, then you got to deal with all that splatter on the screen. Okay, so here's one with a parent folder with a child folder. So we can see, yep, so we can see it there. So if I do -ah, so you can see it's not totally recursive. We have to change into the child folder. Child folder's empty, so maybe it is. Maybe it is. Let's go to let's do touch the force. Okay, and now let's do a du. Okay, yeah, so it is totally recursive. We can see the force in there. Okay, so there we go. The default behavior is to show the usage of every subdirectory, then the total usage of the current directory, including subdirectories. So here we go. There's the usage of the subdirectory in our present working directory, which isn't clear what it is. That's okay. But a subdirectory is this /temp. So that's 4.8. And then including the directory we're in, it's a total of 6 megabytes. In the example above, we can see that the directory temp with a capital T occupies 4.8 megabytes, and the current directory, including temp, occupies 6.0 megabytes. But how much space? Here we go, and this is where it gets into what I was talking about to the AI. But how much space do the files in the current directory occupy, including the subdirectories? So this is going to be different. For that, we have the -s parameter. Tip: keep in mind that the command line parameters are case sensitive. So -lowercase s is different from -uppercase s. So we got a distinction here. So let's go and ask the AI about that. So the question is going to be, so we've got a distinction here. We've got a distinction here. The distinction is between a subdirectory occupying Oh, you know what? I misunderstood this. So in the example above, we can see that the subdirectory temp occupies 4.8 megabytes, and the current directory, including temp, occupies 4.6. But how much space do the files occupy? So altogether it will occupy this much, but for each, but how much do the files occupy? So let's try that. So we've got one file in there, it should occupy 0. If we do a do dash capital S lowercase h, now we see it. Oh. I'm very confused about this. Alright, I don't understand it, so let's work to understand it. Okay, so let's do a du dash uppercase S H. Now let's leave the S out. See, there's too many. Okay, we'll try it here. Dash A. Now I don't understand. Huh. I actually don't understand the dash S parameter. So let's ask the AI. Yeah, let's hear its opinion about it first.
The content you provided discusses the use of the do command in a command line interface to analyze disk space usage. Here's an analysis and my opinion on it. The content explains that the do command is used to determine the disk space occupied by directories and subdirectories. It presents an example where a subdirectory called temp occupies 4.8 megabytes, and the entire current directory, including temp, occupies 6.0 megabytes.
I see.
It then poses the question of how much space the file.
Okay, that's all I needed to know. So basically, the dash S modifies this parameter. When you don't have dash S, and as we can see in my lab, there's dash S is not include. So I ran du 4 times. 1, 2, 3, 4. I ran it 3 times without dash capital S, 1, 2, and then the final time for my 3rd time, and then I ran it 1 time with the dash uppercase S. So what it does is it changes this final number here, which is the total space occupied, including your current directory, when you do not pass it capital S. So as we can see, it's 12 each time I pass it capital S, which is the total space. Now, let's say you don't want to see that. Let's say you want to see how much remaining space is there, or how much space is there in this. Oh wait. I'm trying to think here. So what is it saying? It's saying, so It's saying excluding the subdirectories, how much space is taken up. So, what we're saying is, without the s, how much space is taken up just altogether recursively, including for everything in this folder, how much space is taken up. So we can see that's 12. So if we pass it the dash uppercase s, we can say for everything in this folder except any subfolders, how much space is there. So that could be useful. I'll show an example of it. I'm doing like a mentorship thing. So if we open this up in Bash, and then we do a du on it, we can change that number. Oh, actually, there's no subdirectories in this. Where's the subdirectories? There's the subdirectories. Bash du capital S. Okay, so like here's all these PDFs in here. They're all a part of subdirectories. So we can see the total space occupied by them is 203 megabytes. But let's say I just want to see the total space occupied by things in this folder that aside from the subfolders within it. So now I can pass a capital S, and then I'll do the A and the H as well. Oh, that's interesting. I got a 203. Oh, I got the same value. Okay, well, I got the same value. Was not expecting that. Huh. Alright, so yeah, I guess I don't really understand the capital S parameter. We can see that it changes this bottom one, so I guess I take that to mean that, and we can see the math works out. What is the space of this, not including the space of this? Then we can see, yeah, 6 minus 4.8, so the math checks out. But, yeah, it's kind of not working that same way in practice when I try it out on my lab. And it's really confusing, too, because we see there are no files here. I don't know if they just cut it off for brevity's sake, but this is kind of an unusual amount of space to be taken out by, something with no files. Alright, so I'm going to take a break. When I come back, we'll start reading here. Alright, I'm back, and I am noticing a potential fuzz issue. I've had that before on my videos. Yeah, so it's at about 45 to negative 40. It's just filled up with fuzz. I've had that happen, and I've never actively fixed it before. It just kind of resolved on its own. I don't really know what I can do to fix it. Yeah, so I guess unfortunately I am going to have to just keep going. And if there's fuzz on the line, hopefully it won't be too bad. And as I said, just use like the transcript, use ChatGPT tools. Yeah, if there's fuzz on the line, I apologize. It's outside of my control for this video. Maybe in the next video I can figure out what was happening. But anyways, keeping on going. If you want to keep this distinction between the space used by... let me try this actually before... Alright, so sometimes it can be like there's a loose cable. Oh, that actually like really fixed it. That made it like half of what it was before. Okay, yeah. So sometimes my cables aren't like super tight into my Focusrite, especially the cable in the back. So like when it starts to slip out, then I think I get that white noise there. So whatever I did, it didn't fix it all the way, but it made it half as a problem as it was. Yeah. Okay. So that's perfect. Let's go with it. All right. So if you want to keep this distinction between the space used by the files in the current directory and the space used by subdirectories, but also want a grand total at the end, you can add the -c parameter, which is a very intuitive parameter for total. Cumulative, I guess? I don't know. Let's try it out. So we're going to do du dash capital S, H and C. Let's try the C without the capital S. Okay, so we can get a total. So I would say use C whenever possible, is because it gives you that nice total keyword at the end there. I don't know. You can control how deep the output of du should go with the -dn parameter, where n describes the levels, and it's an uppercase N. Oh, sorry. This is just a placeholder for the. It's just a variable that you'll fill in yourself with the levels you want to go into the directory. So, for example, if you use -lowercase d1 parameter, if you use the -lowercase d1 parameter, it will show the current directory and its subdirectories, but not the subdirectories of those. See the difference below without -d. Okay, so we've got these directories here. So we're seeing a. It's so weird though because it is. Oh, man, that's weird. So if we do a du, it will go recursive through everything. But if we do a du -d1, and it looks like we don't need the space between d and 1 unless it's a typo, then we just see one. Okay, this makes sense. We just see one nested level, so we don't see this one here because it is a directory nested within another directory, so we'd have to have a 2 in order to see that. Please note that even if another dir is not being shown, its size is still being taken into account. You may wish to exclude some types of files from the count, which you can do with --exclude equals pattern in quotes, where pattern is the pattern against which you wish to match. Consider this directory. So du and then the good old fashioned a and the h -a stands for, I think, all. I'm not sure. I actually don't remember. Yeah, it shows all the files. If you don't, it individually counts all the files. If you don't use the -h, the -a, all you see are the directories. So we can see we have this animal.bkup file. So if I do, and then if I do a do -a, yeah. So see. So this is a directory. So with the du, we see the current directory one level deep from the one we are now. Then we see the next directory one level after that. But then we don't see any of the files in the next directory unless we do a -a. Let's do the -d parameter. So we're going to do -d1. And now you can see we don't see that nested directory anymore. All right, so consider this directory. So du-a to see all the files, and then h to see the units of the file sizes. Now we will use --exclude to filter out every file with the .bin extension. Okay, so we wrap it in quotes, and now we use these globbing characters. So any character .bin. So now, notice we did the exclude. So we're just seeing the files, the space used by all the files in this folder recursively. So even if they're in a subfolder, and none of these are, we can see that with the path given here, uh, that don't end in .bin. So we've got 1, 2, 3, 4, 5 files, each with their own different sizes, some with the same sizes, most with different sizes, and then the total amount of space that they occupy, which is 180 kilobytes. Note that the total no longer reflects the size of the excluded files. Yep, and then we don't see the size of the excluded files. And we could use the dash uppercase S to see. Now that's interesting because the slash uppercase S probably would include the. I don't know how that works. I'm really confused about the. So let's do this. Let's talk to the AI. Talking to the AI is good. So we'll highlight this whole section. There we go. So the AI seems to really approve of this writing, which is good. But I have a question for it. So I really don't understand dash S. Can you help me understand it better? Okay. So hopefully this will help.
Certainly. The S option in the do command is used to control how the command calculates and displays disk usage. It stands for separate or single depth, and its primary purpose is to show the disk usage of the specified directory or directories without including the sizes of subdirectories within them. Here's a clearer explanation of how the S option works. 1. Without S**, when you run the do command without the S option, it displays the disk usage of the specified directory and all its subdirectories, providing a total for the entire directory tree. This means it includes the sizes of all files and subdirectories within the specified directory. Example: $do h/path/to/directory. The output will list disk usage for each subdirectory and provide a total at the end that includes everything within the specified directory. 2. With S**, when you include the S option with the do command, it calculates and displays disk usage for the specified directory or directories but excludes the sizes of subdirectories. It only shows the sizes of files and immediate subdirectories of the specified directory or directories. Example: $do sh/path/to/directory. In this case, the output will list disk usage for the specified directory and its immediate subdirectories, i.e., one level deep, but won't include the sizes of subdirectories within those immediate subdirectories. This is useful when you want to focus on the immediate contents of a directory without diving deeper into its subdirectory structure. In summary, using S with the do command allows you to see the disk usage of a directory while excluding the sizes of its subdirectories. It's particularly useful when you want to analyze and manage disk space usage at a shallower level, focusing on the contents of a directory without getting overwhelmed by the sizes of all subdirectories within it.
Okay, so next question is dash D1 equivalent to dash uppercase S? Oh, okay. No, it's not.
No, D1 is not equivalent to S in the do command. These two options serve different purposes. 1. D1*, this option specifies the depth to which the do command will display disk usage information. When you use D1, it will show the disk usage of the current directory and its immediate subdirectories, one level deep, but not the subdirectories within those immediate subdirectories. It's a way to limit the depth of the directory tree that do analyzes. Example: $do hd1/path/to/directory. This will provide disk usage information for the specified directory and its immediate subdirectories but won't include the sizes of subdirectories within those immediate subdirectories. 2s*. This option, as explained earlier, is used to show disk usage while excluding the sizes of subdirectories within the specified directory or directories. It focuses on the immediate contents of the directory without including subdirectories. Example: $do/path/to/directory. This will provide disk usage information for the specified directory and its immediate subdirectories but won't include the sizes of subdirectories within those immediate subdirectories. In summary, both D1 and S limit the depth of the do command's analysis, but they do so in different ways. D1 focuses on the immediate subdirectories at a specified depth, while S focuses on the immediate contents of the specified directory without including subdirectories.
Okay, so the next question is, can you think of -s as -d0 to understand -uppercase S more intuitively? Okay. That is what it is.
Yes, you can think of S as an equivalent of D0 to help you understand it more intuitively. While the S option isn't technically the same as D0, conceptually, they achieve a similar result. Both options focus solely on the specified directory itself without including any subdirectories in the output. Here's how you can view it. S, show disk usage for the specified directory, level 0, excluding subdirectories. D0, limit the depth of the output to level 0, effectively showing disk usage for the specified directory itself and not its subdirectories. So, in practice, if you want to see the disk usage of a directory while ignoring its subdirectories completely, using S or D0 would provide a similar result.
All right, so now I understand it. Let me see if D0 is valid. It is. Okay. So let's see if I get the same result with S. Oh, so I get a different result with S. Okay, well that's interesting. Uh huh. And then C I get something else. C I get 12, but huh. I mean, it's just the total size of everything, with the subdirectories missing. So like, without these constituting the total space that we have, it's the remaining space of the total. So it's like, what does D0 here? Um, like, what does that take up of the space that that is left over after these take up space? That's basically what it means. It's not that difficult to understand. All right, so the next part is checking for free space. So du works at the files level. There is another command that can show you disk usage and how much disk space is available at the file system level. This command is df. The command df will provide a list of all the available already mounted file systems on your system, including their total size, how much space has been used, how much space is available, the usage percentage, and where it is mounted. So here we've got DF. Now these show file systems, and that's something I kind of didn't realize before, because um, this syntax here is like a that's a partition, not a file system. So like, I would expect to see something like ex4, ext4 showing up there. I'm kind of surprised we don't see it anywhere, it looks like. So yeah, surprising output for me. EFI, that, the boot file system, but even that, it's a like that's a boot partition, right? So yeah, kind of confusing output there. Okay, so however, showing the size in 1 kilobyte blocks is not very friendly. Like on DU, you can add the -h parameters to get a more human readable format. Alright, let's do that in the lab. -h, there we go, looks good. You can also use the -i parameter to show used/available inodes instead of blocks. So, I'm not sure what the difference between an inode and a block is. We can ask the AI. So, what is the difference between an inode and a block? This is quite a few differences. Let's hear them all, because this is, if it's such a, yeah, it's a fundamental concept. We gotta learn the fundamentals. That's really important.
In a file system, both inodes and blocks are fundamental concepts, but they serve different purposes and are used to manage and store data differently. Here's a breakdown of the key differences between inodes and blocks. 1. Purpose. Inode, an inode, short for index node, is a data structure used by the file system to store metadata about a file or directory. This metadata includes information such as file permissions, ownership, file type, timestamps, creation, modification, and access times, and pointers to data blocks that actually store the file's content. Block. A block refers to a fixed size chunk of data storage within a file system. Blocks are the units in which data is stored on the storage medium, example hard drive or SSD. 2. Contents. Inode, it contains metadata about a file or directory, not the actual file data. The inode points to the data blocks where the file's content is stored. Block, it contains the actual data of a file. Multiple blocks may be used to store the complete data of a file, depending on its size. 3. Numbering and identifiers. Inode, each file or directory is associated with a unique inode number, I number. Inodes are used to uniquely identify and manage files and directories within the file system. Block. Blocks are typically identified by their position or offset within a file, and they are managed as part of the file's data structure. 4. Role in file system. Inode. Inodes are
I wasn't listening. I was distracted. So here's my next question. Let's pay closer attention to this.
In a file system, both inodes and blocks are fundamental concepts, but they serve different purposes and are used to manage and store data differently. Here's a breakdown of the key differences between inodes and blocks. 1. Purpose. Inode, an inode, short for index node, is a data structure used by the file system to store metadata about a file or directory. This metadata includes information such as file permissions, ownership, file type, timestamps, creation, modification, and access times, and pointers to data blocks that actually store the file's content. Block. A block refers to a fixed size chunk of data storage within a file system. Blocks are the units in which data is stored on the storage medium, example hard drive or SSD. 2. Contents. Inode, it contains metadata about a file or directory, not the actual file data. The inode points to the data blocks where the file's content is stored. Block, it contains the actual data of a file. Multiple blocks may be used to store the complete data of a file, depending on its size. 3. Numbering and identifiers. Inode, each file or directory is associated with a unique inode number, I number. Inodes are used to uniquely identify and manage files and directories within the file system. Block. Blocks are typically identified by their position or offset within a file, and they are managed as part of the file's data structure. 4. Role in file system. Inode. Inodes are crucial for maintaining the structure and organization of the file system. They keep track of file attributes and provide pointers to the actual data blocks. Blocks are where the actual file content resides. They hold the binary data that makes up files. 5. Size. Inodes are relatively small data structures, typically a few hundred bytes in size, and a file system has a limited number of available inodes. Block sizes vary depending on the file system and configuration but are usually larger than inodes. Block size can range from a few hundred bytes to several kilobytes or more. 6. Management. Inode. File systems maintain an inode table that keeps track of inodes, their usage, and the allocation of inodes to files and directories. Block. File systems manage data blocks and their allocation to files through data block allocation tables or bitmaps. In summary, inodes are used to store metadata about files and directories, while blocks store the actual data content. Inodes are used to manage and organize files and directories within the file system, and they provide pointers to the blocks where the data is stored. Understanding the distinction between inodes and blocks is essential for effective file system management and data storage.
Alright, so nodes store the metadata about the files and directories. Blocks store the actual content. It's important to know the difference between that. So that was a fundamental. So let's take a look at what the other fundamental things are. These are pretty good. Yeah. So I already knew all this. I'll just save it. Oh, or on site. Uh. Please do not. Include on site. Okay. All right. Yeah. All right. Well, it's just generic stuff. We could get that from free ChatGPT 3.0. Really nothing super insightful in my opinion. So yeah, you do -I to get the inodes, which shows you the metadata for the file. One useful parameter. Let me try -im to see if I can get the yeah. So let's follow along with this. So we're gonna do df. All right, there we go. We're gonna do df -h. All right, we get it in the human readable. Now we're gonna do df-i. df-i. All right, so now we get the I nodes showing up. So let's do a df-i-h. I'm having trouble typing today. So df-ih. And there we go. Now we get the inodes in with the units. So there we go. That's what I thought. I didn't know what those numbers represented, if they were file sizes or like, you know, the number of nodes, whatever their sizes would be. But it's just the same as the blocks. You'll notice that the numbers are a lot smaller than the blocks. So if I take the I out, the blocks are larger. That's because the blocks are the actual data in the file, and the inodes is just the metadata. So one thing I'm not clear is if the full size of the file includes the inodes and the blocks. Not clear about that, but anyways, one useful parameter is capital T, which will also print the type of each file system. Okay, good. This is what I was expecting to see. Let's see how many types of file systems I have on mine. df-h, or -h for human readable, and then uppercase T. So there we go. So we've got quite a few file systems on here. We got a VFAT. That's interesting. Yeah. Here's the ext4, which is kind of what you would expect to see on Linux. Knowing the type of file system, you can filter the output. Knowing the type of the file system, you can filter the output. You can show only file systems of a given type with -T type, or exclude file systems of a given type with -x type, like in the examples below. So excluding TMPFS, temp file systems, we can do -x, and then that will exclude. So df space -h, you want those units still, x tmpf. So let's exclude a file system from mine. We'll just exclude the same one. So -hx tmpfs. There we go. Alright, so showing only the ext4 file systems. Now you can do the opposite of excluding. You can only include with a -t. We can't use a -i because they stand for the inodes, but T stands for type. So the type of file system we want to see is an ext4. Let's do that in my lab. Same thing. df-ht ext4. There we go. Alright, and then the thing is, you don't even have to... You can do that without the parameter that makes them show up, which is the capital T, which is kind of neat. But if we add the capital T back in, I think we have to do it separately like this. Yeah, there we go. Now we got that type column showing up, but you can filter it out by type even if you don't have the type column in the output. Alright, so you can also customize the output of df, selecting what should be displayed and in which order, using the --output equals parameter followed by a comma separated list of fields you wish to display. Some of the available fields are source, the device corresponding to the file system type, the file system type, size, the total size of the file system, used, how much space is being used, avail, how much space is available, %, the usage percentage, and target, where the file system is mounted, the mount point. If you want an output showing the target, source, type, and usage, you can use df -h output equals target, source, file system type, and % used. Yeah, so I want to see that. So let's do that. We can include custom columns with --output equals, and then we have to know this list of fields. Maybe it's in the man. I think I saw it there. Okay, I don't see it there. Oh, here we go. So yeah, output. So use the output format defined by field list, or print all fields. So we should have some help for field list. Here we go. So field list is a comma separated list of columns to be included. Valid field names are source. There we go. So easy as 1, 2, 3. All you got to do is read the man page, which can be tricky sometimes, honestly. Like, sometimes it's difficult to make sense of what you're reading in a man page, but hopefully that part made sense. That wasn't too tricky. So let's do and let's create an output showing the target, source, type, and usage. I guarantee you that something like this is going to be on the exam when it comes to like a real world hands-on simulation or something like that, similar question. Guarantee you they're going to ask about this. So all you got to do is do man, and then make sure you know the man file. Make sure you notice this output, and then they'll yeah, I should be able to hit that one out of the park. I can't emphasize enough how important it is to get used to using help. If you're just memorizing commands, um, like I think memorization can be really important, and I've used Anki a lot and memorized a lot of things in my own career, and it's really helped me out. But at the same time, memorization can only take you so far, and what's more important than memorizing something is being able to figure out something that not only do you not have memorized, but that you've never been exposed to before. So, like, there's situations where you didn't have the chance to memorize something because you'd never seen it before. How you do in that situation, I think, is really important, and that's where things like knowing how to access the help menu, knowing what help means when you read it. That's the difference between success and failure in that situation. All right, so df can also be used to check inode information by passing the following fields to dash dash output equal. Okay, so I total, the total number of inodes in the file system. I used, the total number of used inodes in the file system. I avail, the total number of available inodes in the file system. I percent, the total number of used inodes in the file system. And inodes, as we saw, is just the sizing information for the metadata, but not the actual data that's stored itself. So, like, for example, the permissions on the file would be inode data. All right, so for example, now we're going to look at some inode information, and I'll type this out and do this in my lab. Source, type, I total used, so there we go. Alright, so maintaining EX2, EX3, and EX4 file systems. To check a file system for errors and hopefully fix them, Linux provides a FSCK utility. Think of file system check, so file system CK check, and you will never forget the name. In its most basic form, you can invoke it with file system check command fsck followed by the file system's location you want to check. So we've got a file system on /dev/sdb1. So storage disk B partition 1. So the command is file system check fsck space /dev/sdb1. Warning, never run file system check or related utilities on a mounted file system. Oh, okay. Well, I'm not going to do it in my lab then. If this is done anyway, data may be lost. And we can see what we get back are 3 lines here. Yeah, so you can't get this information if it's mounted unless you are okay with losing the data, which you are probably not. Just unmount it first. All right, so FSCK, file system check itself, will not check the file system. That's counterintuitive. It will merely call the appropriate utility for the file system type to do so. In the example above, since a file system type was not specified, FSCK assumed a ex2/3/4 file system by default and called E2FSCK. So it assumed the 2 apparently. I guess, I don't know. To specify a file system, use the -t option, lowercase t, followed by the file system name, like in FSCK space -t space vfat space /dev/sdc. Alternatively, you may call a file system specific utility directly, like fsck.msdos for fat file systems. Tip: type fsck followed by tab twice to see a list of all related commands on your system. Alright, so I can do that one without ruining it. Let's do that. FSCK for file system check, tab twice. And there we go. We've got it for all the different kinds of file systems. EX2 through 4, FAT, MS-DOS, VFAT, FXS, MiniXS, BetterFS, and then this one I've never seen, CramFS. But that disk I have that I wanted to slot in, I think probably the reason why it's not working is it's not formatted with a partition in a file system. So really want to look at that disk again sometime. You can see the disk that I have already in there, the dev SDA. If we can do a -t. Oh wow, okay. What? Oh, okay. Because you have to pass it. Wait, I'm confused. Oh, okay. No, this is yeah. So that partition is the UDEV partition, but this partition with all of the if we do a -m or sorry -h for human readable is what I meant to do. We've got oh wait what? That's a small partition. I'm confused. I mean, my home lab is messed up. Don't get me wrong. It's like my home lab needs some work. Like it needs to get the storage figured out. It needs to get the storage expanded on it. And if this doesn't make sense because it's yeah, already like 17% is used. So like uh, yeah, so it's like 17% of it's larger than a gig drive. It's like an 800 gig drive. So like yeah, I don't know why it's so small there. All right. So file system check can take some command line arguments. These are the most common. -A. This will check all file systems listed in /etc/fs tab file system table. Let's try to cat that out. Okay, so this is a important file. Don't mess up this file. Yeah, so we've got the swap in there. Yeah. All right, -C displays a progress bar when checking a file system. Currently only works on ext2/3/4 file systems. -N. This will print what would be done and exit without actually checking the file system. -R when used in conjunction with -A. This will skip checking the root file system. -V. Verbose mode prints more information than usual during operation. This is useful for debugging. Alright, so the specific utility for EX2, EX3, and EX4 file systems is EX2 file system check. So that's like called when you just use a file system check, I guess. and then you do a dash T for type, if I remember correctly how this works. Yeah, dash lowercase t, and then you pass in the type. So that's you're calling like one of these basically. So it's also called file system check dot so fsck dot ext2, kind of like how we remembered for the other command. I forget what the command was. I think it was just in that lesson where there was just a lot going on in that lesson. So um, uh, yeah, so let me do a control F to make sure I've got my place saved here, and then I'll go up to the last lesson and try to remember what that ext4. Yeah, there was just, oh, I see. So this is a command to make the file system. So it's mkfs, and it's basically a similar command to this command we're learning here, which is a command to check the file system after it's already been made. Very similar syntax. Okay, so it's also called fschk.ex2, fs or ck, there's no h, dot ext3, and fsck.ext4. Those three are merely links to e2 FSCK. So the 2 doesn't stand for the version of the ext. Um, they're just links back to this command, which can process 3 and 4 as well. So by default, it runs in interactive mode. When a file system error is found, it stops and asks the user what to do. The user must type Y to fix the problem, N to leave it unfixed, or A to fix the current problem, and all subsequent ones. Of course, sitting in front of a terminal waiting for E2FSCK to ask what to do is not a productive use of your time, especially if you are dealing with a big file system. So there are options that cause E2FSCK to run in non-interactive mode. One of those options is dash lowercase p. This will attempt to automatically fix any errors found. If an error that requires intervention from the system administrator is found, E2FSCK will provide a description of the problem and exit. Dash lowercase y. This will answer y, yes, to all questions. Dash lowercase n, the opposite of dash y. Besides answering no to all questions, this will cause the file system to be mounted read-only, so it cannot be modified. That might be useful. Dash lowercase f forces E2FSCK, which remember is what all these other commands are. It just calls that command to check a file system even if it is marked as clean. For example, has been correctly unmounted. Okay, so even if it doesn't seem to need a check, you can check it anyway. All right, so this is another mega lesson like the last one. So I think, so I gotta be mindful of the clock. Um, Let me see where I just finished reading. Yeah, so the next one is fine tuning an EXT operating system. It might be a good place to stop depending on what the clock says. Oh yeah, we're well over the hour. So I think I'm gonna stop here. There's just a lot. This next section is a complete beast as well. So yeah, I want to keep these around the hour mark. So it's a good stopping spot. So I'm gonna keep my place here. So colon. And then, yeah, text equals, okay. All right, looks good to me. So, yep, that's it for this video. Thanks for watching, and see you in the next one.